Hello everybody, my name is Austin Harris and today we will be finding the index of refraction of this acrylic prism by using the properties of total internal reflection. Total internal reflection happens when the refracted ray from a laser of a single wavelength completely reflects off the boundary between objects with a higher and lower index of refraction, as we can see here. To analyze the critical angle necessary to create total internal reflection, we will first trace this isosceles triangle and all rays passing through and out of it. I've placed a piece of paper underneath the triangle so that I can trace the triangle, the incident rays, and the reflected rays. It's important to trace carefully here because small errors here can lead to large percent discrepancy at the end. Excuse my head. After we've carefully marked entry and exit points for all the rays, we can use a ruler to make straight lines between the points. Next, I'll be using a protractor to mark the angle normal to the reflecting surface. This is important because the critical angle for total internal reflection is always measured between the incident ray and the normal. Next, I'm going to grab my protractor again and measure the critical angle as accurately as I can. I measured this critical angle to be about 44 degrees. I have set up 4 cases to describe what happens during total internal reflection. The left side of the vertical line is the acrylic material of the prism, and the right side is air. As you can see in case 1, the incident ray is normal to the surface, so there is no refraction and no reflected ray is present. An important note to keep in mind is that in order for total internal reflection to occur, the light ray must be traveling from a higher index of refraction to a lower index of refraction, which I've noted in the top right corner. In case 2, you can see that with a small incident angle, the refracted ray bends away from the normal a little bit, and the reflected ray is quite weak. I made a note about the reflected ray being present in imperfect prisms because in an absolutely perfect prism, all the light would either be refracted or reflected, but not both. In case 3, as the incident angle increases, the reflected ray gets stronger as the refracted ray gets weaker and approaches 90 degrees from the normal. Case 4 represents what happens during total internal reflection. The refracted ray refracts to 90 degrees from the normal. In other words, it is perfectly parallel to the boundary between the acrylic and the air. In a perfect prism, all the light from incident ray would be reflected, but with an imperfect prism, the intensity of the reflected ray is slightly less than that of the incident ray. Judging from this representation, total internal reflection happens when theta 2 reaches 90 degrees. At this point, theta 1 is called the critical angle for total internal reflection. Snell's law states that the index of refraction of one material times the sine of its incident ray is equal to the index of refraction of the second material times the angle of refraction. This is written in the top left corner as n1 times sine of theta 1 equals n2 times sine of theta 2. Since total internal reflection happens when theta 2 equals 90 degrees, and since the sine of 90 degrees equals 1, it's a matter of simple algebra to solve for theta 1, which is the critical angle. If you take a look at the equation for the critical angle, you notice that part of it includes the inverse sine of n2 over n1. Recall that sine doesn't output values above 1, so the inverse sine cannot accept input values above 1. This is mathematical evidence that total internal reflection will not happen when the light ray is traveling from a lower index of refraction to a higher one. We're interested in solving for the index of refraction of the acrylic block. Simply skip step 4 in the algebra and go directly from step 3 to 5. It's now time to plug and chug. Simply plug in the index of refraction of air, which is 1, and plug in our measured critical angle, which was 44 degrees. I got 1.44 as the index of refraction for the acrylic block at this wavelength of light. With an imperfect prism and grade school level measuring devices, the percent discrepancy between the experimental and theoretical index of refraction of acrylic, which is about 1.49 at this wavelength of light, was 3.4%. I would say that's pretty good. Thanks for watching.